Hello everyone and welcome to this online course of aquatic geochemistry. We have been discussing a few tracers for aquatic systems and we have been discussing the various applications of stable water isotopes in our previous few lectures. And in this particular lecture, we are going to discuss about the carbon isotopes and its applications. So, in aquatic geochemistry, carbon isotopes is often used as a tracer to understand mostly origins of organic matter from the different terrestrial ecosystems, and of course how it is interacting in a given system. So, if I show you a periodic table like this, and we will see that a lot of isotopes are used and their applications are generally can be clubbed into certain categories. For instance, this group, this group of C, N, O and here hydrogen, this group is of course, as you can see, is essential and fundamental in all life forms. So, we are made up of a lot of C, a lot of N, O and H, and this is the reason that even the simpler forms, it is not just V, which means larger organisms and complex animals, it is also in plants and it is also in single cellular and multicellular animals across the entire globe. So, therefore, their applications are more of understanding biological processes, how biology interacts with water, how sources of different carbon, of different types of organic matter, how that is moving in and out of an aquatic system. We use these particular isotope systems to try to trace that. So, particularly these isotope systems, now it is not that these are the only one, but these are the more traditional isotopes that has been used, and of course, it can be clubbed as suitable as as according to the the problem that we are trying to solve. It can be clubbed with any other isotope. So, there can be sulfur and oxygen isotopes, or there can be some other, for example, there can be sodium isotopes or there can be iron isotopes. So, depending on what is your objective and what is your what is your systems, like if it is a soil terrestrial system or if it is a terrestrial aquatic system, or you are looking into an extremely expansive system such as the critical zone, then you need multiple tracers to give you a kind of holistic picture, because different tracers they signify different kinds of processes. One particular system may not be able to give you the entire information. So, therefore, particular tracers are required for certain fundamental understanding, and then there are a different set of isotope systems that can be used as supporting evidence. So, often in studies you will see that there will be multiple traces. If it is stable isotopes, you will see there will be carbon isotopes, which can be, if it is terrestrial origin, then there can be nitrogen, carbon, oxygen, or if it is any environment where there is a lot of reducing activities going on, then there can be sulfur isotopes, there can be oxygen isotopes, there can be nitrogen isotopes. So, therefore, what we observe is that by using multiple isotope data sets, we get a better understanding of the of whatever is the process happening, or the source sink balance, or the basically to understand and answer the questions that we are trying to ask. And that is mainly because these traditional isotope systems, they have a significant natural variability. So, this kind of natural variability and the kind of processes that can lead to these kind of variabilities is important to address. For example, if you see some variation in oxygen isotope, then what are the factors that influences oxygen isotope? There can be temperature. If it is in water, okay, if it is in water, meteoric water, then I am talking about, and it can be temperature. If you see this is in, so basically what are the parameters? If you are investigating temperature, you will use another system that is very sensitive to temperature. If it is sensitive to biotic processes, okay, for instance, if you are particularly looking into decaying of organic matter and things like that, so you will look at carbon, you will look at nitrogen, you look at sulfur. So these kind of, if all of them tell the same storyline, then you understand, okay, fine, this is what it is. We have got multiple lines of evidence to show me this, because theories based on a single isotope data set or of limited data sets becomes difficult to trust, okay, because of the natural variability and the huge range of processes that can lead to its variability. Therefore, we use multiple isotope systems specifically when we are using this group, that is C, N, O and H, okay, because of the huge variations that can be there in biological processes and its interactions in the natural world. And here we are using these isotopes. It's it's extremely useful for understanding two things. One is paleotemperature, second thing is paleoprecipitation. So basically the paleoclimate. So because of its usefulness and applications in understanding Earth's past history, therefore drawing the correct conclusions is very important. So therefore we use multiple types of traces. For instance, if we are looking for weathering related activities, a simple strontium isotope study can be able to give you enough information. Because of the nature of variability, they are radioactive isotope systems. Their variability is very limited. It is only due to decay or mixing. No other biotic process, any other kind of reactions is going to change the strontium isotope data. So therefore, in weathering studies, you will see maybe just strontium isotope data, or maybe just samarium niobium isotope data, or just osmium data. Okay. So there is a different story, because their variations is far less, their variability, the range of natural variability is far narrower. So we have more more confidence that if there is slight variations, then it is this process, it is indicating this process. But that is not so with carbon, nitrogen, oxygen, hydrogen isotopes. Okay. So therefore these isotopes are used in multiple groups, whereas radioactive isotopes such as strontium, samarium, neodymium, or rhenium, hafnium, osmium, and lead isotopes, uranium isotopes, they are used generally as very single powerful isotope systems. Their applications are very to the point. So therefore we do not have a lot of possibilities of conflict. Okay. There are other group of elements that can show us particular things. For example, in this world where we are constantly modifying our natural environment, we are constantly modifying the natural aquatic system, there is there is always a need to understand how much we are influencing, either through direct interventions or indirectly. Indirectly meaning either through the atmosphere or through the soil or something. So that is like an indirect stress that we are giving on the system, or something can be happen later. So that we called something we did it today, but it will not show today, it will show maybe 30 years or 40 years down the line. So such kind of legacy activities. So when we talk about our contribution, our our interventions and their impact on natural cycles, often some particular elements are used to understand these impacts, and we are particularly targeting how to separate out the anthropogenic impact versus the natural geogenic controls. Okay. So, for that we are going to use particular isotope systems. For example, mercury is widely used, lead is another extremely used isotope system, uranium is another extremely used isotope system. So, for particular uses, okay, for particular questions, might be different traces. Okay. If in your study you are looking into a lake, or you are looking into a river, or you are looking after any water body, and you are trying to find out, okay, what is the natural and what is the anthropogenic contribution, you can start looking into whether you can use lead or whether you can use uranium. So, then it becomes very particular. You are not going to use all the isotope data, or go around seeing whether nitrogen can be measured and things like that. You have very specific targets. To fulfill those targets, you are going to use these particular elements. Okay. Then certain, if you are trying to understand certain isotope systems, for instance, I am trying to investigate how iron isotopes fractionate, and that is irrelevant for the processes, but I want to measure how iron is fractionating. Okay. So, how it is fractionating with the different biotic processes, or with the inorganic process such as pH or redox related processes, or due to anthropogenic contribution. For these type of understanding, many times we are going to use this, because this is both geogenic, that means they are extremely high contribution from natural weathering processes, and they are there almost ubiquitous in all the aquatic systems from natural weathering. But they are also very reactive, or certain ones, not all, but certain like iron, manganese, chromium, they are also reactive to some biotic processes. Okay, they act as enzymes, coenzymes, and they get incorporated with the biomass. So, therefore, there is a there is a continuous uptake and giving out process that is going on in the aquatic systems. So, they are they are being exchanged at a much larger scale, and not only this, even these elements, okay, these elements that is lithium, sodium, magnesium, potassium and calcium, not strontium. So, these are also getting exchanged with the biomass and all that. So, these kind of isotope systems we are going to understand. I mean, these isotope systems are still, we are doing research, we are trying to investigate how a particular isotope system behaves during a particular process, whether that behavior is uniform or whether it is behaving differently in different aquatic systems, whether it is changing in with temperature, with any other parameter. Is it species, that is a particular biotic species specific. So, such kind of studies are still going on, and they are continuously evolving, right. So, that is why they fall under the non-traditional stable isotope system. That means, we are still trying to understand how these isotope systems are behaving in the natural world. So, we cannot use them with the current understanding in particular systems where it is well established. We can use it as a tracer, but it is mostly to understand sources and some kind of dominant processes. But there are still a lot of studies that is left to be done, and therefore, we we say that these are non-traditional isotopes, because their their understanding is is still ongoing. How they are evolving in the different marine ecosystems, how they are evolving in freshwater ecosystem, in different kind of geological settings, different kind of climatic settings. We are still studying that. Okay. and of course, there are other isotopes that we use for dating and all that. Now, so coming down to this particular isotope system, that is carbon isotopes. And as I have already mentioned, that carbon we are mostly interested in because of its extreme importance in contributing to the global climate, okay, because there might be other gases, there might be other other elements also that requires significant monitoring. But we have noticed significant changes in ocean acidification, in our atmospheric CO2, to know that this human driven CO2 rise in the atmosphere has altered the climate, and how this altered climate is going to affect life in future, not only to us, but life over in general in the planet Earth. To understand better understanding, we have to look back. We have to look back at what had happened in the past, how past changes have shifted the ecosystems, how it has changed things and made it what it is today. Now, when talking about carbon isotopes, okay, we are trying to therefore understand the carbon cycle, okay, because we are going to see how much it is moving from one reservoir to another, because as you know that carbon dioxide in the atmosphere is a very small fraction, okay, the number is very small, okay, but it is the fluxes involved that is immense, and that is what is very important, how the fluxes are changing. It is not the ultimate number. So, if I tell okay today the CO2 is this much, it has increased to this much, it is not the absolute numbers, but what I am trying to understand is how the fluxes through the cycle has changed, okay, whether things that were happening in the past in equilibrium in the past is still active today. If it is not active today, what will happen? What will happen that can can be threatening or be promising, or so that kind of understanding. So, even though some numbers look very small to you, it is not the reservoir numbers that we are working on. It is not the atmospheric carbon dioxide as a reservoir that we are thinking of. It is a huge fluxes that is moving across the reservoirs in a very short time scale is what we are looking at. Okay. So, in generally we consider that there is a stable and there is a steady state in every elemental cycle. Elemental cycle means how an element moves across different reservoirs through the earth. So, there is rocks, there is mantle, there is crust, there is water, there is atmosphere, there is biomass. So, there are different components of earth. So, how a particular element, as you can see in this figure, that it shows the movement from atmosphere to the surface ocean to the deep ocean, okay, and from the deep ocean where can it go? It can either get precipitated out, it can form the sedimentary rocks, or it can move to the inside the it can get subducted and it can move inside the mantle. From the mantle it can come out as gases, or maybe the the terrestrial biomass that got fossilized and now it is being released back from fossil fuel burning and all. Then there is a significant amount of carbon that is trapped as land biota. Okay. There can be different reservoirs, okay. It can be in the soil, it can be in the biomass. Okay. So, there are different reservoirs, and the numbers that is shown in the bracket shows you how the isotope variations are, how varying the isotopes are. And if you see the flux and if you see the fluxes and if you see the reservoir number, you will see that mantle is one of the largest reservoirs in terms of carbon. Okay. Mantle has a huge reservoir of carbon. Similarly, carbonate in the sedimentary rocks, they are a huge reservoir, and it is far less as compared the atmosphere seems like a very small reservoir in front of them. But what we are changing is the fluxes. So, it is not the reservoir we are seeing, it is the fluxes and what that particular fluxes could do in a very short time scale that we are worried about. So, let us see some general information and then we are going to look into some one particular application. So, in general there is a huge annual incorporation of carbon dioxide during plant respiration. Of course, so plants will respire, carbon dioxide is coming into the atmosphere, that is how it is getting into the atmosphere majorly. Where is this coming from? This is coming from the decomposition of the plants and organic carbon in the soils, and it is getting again recycled. So, again the new plants that is forming, they are again going to take up that carbon and again it is basically getting recycled, and the plant will again pick up carbon dioxide from atmosphere and move it back into the biomass. So, there is a huge cycle, terrestrial cycle of carbon dioxide between the plants, the soil and the atmosphere. Okay. So, that is a huge flux. Another huge flux is between the atmosphere and the surface ocean, where the carbon dioxide is getting dissolved in the water and is it is getting trapped in the form of the bicarbonate form. So, it is called the DIC, okay, that is the dissolved inorganic carbonate, and which is majorly as bicarbonate. Okay. So, there is a continuous uptake of atmospheric carbon dioxide in the surface ocean, and between the surface ocean and the deep ocean there is a large and almost like a steady state balance of flux. That means, from the shallow ocean whatever is sinking, it gets precipitated out, and similarly if there is anything returning back, that means if there is any organic matter decay, then from the deep ocean also those gases get released back into the surface ocean. So, there is a continuous and nearly balanced flux between the shallow ocean and the deep ocean. Okay. But what is changing is the contribution from this reservoir, which is called the fossil fuels, into the atmosphere, because when this is a one sided process, no atmospheric carbon dioxide is going back into the form of fossil fuel. So, whatever is being trapped in that particular reservoir is just getting released into the atmospheric reservoir. The fluxes between the other reservoirs, that is the carbonates, mantle, organic carbon, they are orders of magnitude lower, okay, and their relevance is only in terms of long term variation. Okay. Their relevance only comes in long term variation because of this balanced nature. See, from the shallow ocean to the deep ocean, due to this balanced nature, the flux becomes very insignificant as compared to the flux from the fossil fuel to the atmosphere. That flux is a one way flux. So, therefore, we are worried about it. The flux from the mantle to the atmosphere, that is mantle degassing, is extremely long process, very long time scale. So, therefore, again it is only considered when we are thinking in millions and billions of years of time scale, that is across the entire path Earth's history. But if you are looking into rapid changes happening in the climate across the globe, what becomes important then? Looking into the flux in the terrestrial ecosystem and the fluxes from the fossil fuel to the atmosphere. This is the flux that we are more interested in. Okay. So, this is a table that shows the reservoir, the mass, okay, and also the delta 13C composition. Okay. So, here you can see there is atmosphere, there is ocean, there is land plants, there are soil humus, sedimentary inorganic carbonates, organic carbon. In the silicic crust, how much carbon is there? In the mantle, how much carbon is there? And everywhere you can see how the isotope compositions are changing. Okay. You can see how the isotope compositions are varying. So, as a rule, what do we see? We know that the formation of organic matter is a non-equilibrium process. Of course, it is a non-equilibrium process, because there is no way that it can happen in equilibrium with the water or something like that. Okay, it is a kinetic process. So, whenever there is some kind of, say, like the cell wall is getting generated or the cell mass is being generated. So, this is not an equilibrium process. Okay, it is not an equilibrium process, and of course, it is mediated by kinetic processes, because during this formation reaction the lighter isotopes move faster, as I have already showed the kinetic fractionation. So, between the heavier isotope and the lighter isotopes has a faster velocity, that means they reach to the spot of the reaction faster than the heavier isotope, and therefore, they get preferentially absorbed also. So, this organic matter is higher in 12 carbon composition as compared to 13 carbon. Therefore, this is my reservoir of low delta 13C. As compared to that, 13C is concentrated in the more oxidized, more stable forms, because carbon and oxygen, the CO bond is very strong. This covalent bond is very strong. Okay. This covalent bond being a very strong stable phase, my 13C always is going to prefer any kind of oxidized form. So, CO, CO2, these are the more oxidized form as compared to the organic matter, which is some with some formula of CH, some another nitrogen, oxygen, some, but it is not in its oxidized form, like that is like CO2, okay, simply oxidized. So, this is my reservoir, the CO2 is a reservoir which is more oxidized, and therefore, will have a higher delta 13C value. Okay. Now, the delta 13C of carbonates, okay, when the carbonates are forming, then there is a difference. Okay. The delta 13C of carbonates, that is incorporated, that is the shells of animals, okay, that is controlled by the incorporation of bicarbonate, and not to the amount of carbon dioxide that is related to metabolism. That is for most, that is for particular species. For particular species, we know that the delta 13C values are mostly related to the bicarbonate that is present in the aquatic system. Okay. So, the delta 13C values is correlated with the DIC values of that prevailing water, okay, and it is not going to change with the metabolism, okay, because it is directly not interacting. The carbonates is simply trying to precipitate as carbonate. So, that is not going with the metabolic activities. But if it is getting respired or something like that, if you are measuring the carbon dioxide that is getting respired, then the respired carbon dioxide has lower delta 13C and delta 18O values than the inorganic bicarbonate. Why? Because my body is made of less 13C. So, when I am respiring also, the carbon that I am releasing is 12 carbon enriched and 13 carbon depleted. So, therefore, the lower values, and similarly for 18O also, I am more 16 oxygen enriched as compared to 18 oxygen. So, there will be a lower value of delta 13C and delta 18O if there is some metabolic interaction if there is some respiration going on. Okay. And if you notice that the values are very low, you will note that there might be some impact of metabolic activities on that particular carbonate. Okay. But other than that, the delta 13C of marine carbonates, that is precipitated out as sedimentary rocks, not from shells of animals, not through animals, but just simply as calcium carbonate precipitating in the form of, first it will form lime and then limestone and all. If it is just simply precipitating, then that is at near equilibrium with the dissolved bicarbonate composition. So, that isotope composition will reflect the dissolved bicarbonate composition. Okay. So, here there is no organism to change the delta 13C values. So, whatever the delta 13C of inorganic carbonates are is at equilibrium with the bicarbonate values. Okay. It is with equilibrium with the bicarbonate values. And the delta 13C of terrestrial organic matter comes from the carbon dioxide respired by plants or other photosynthetic organisms. So, if you are looking into soils, and if we are measuring soils, you will see that the delta 13C values will be very low, because the soil, it is uptaking or it is the decayed matter is there. So, therefore, that will show the organic matter composition, which is generally of negative or lower delta 13C composition. Also, the delta 13C of carbonate or organic matter that is related to the delta 13C value of its source can and will show the overall carbon cycle and the local productivity. So, for example, you look into a system which is like a soil, very old soil, so it is called a paleo soil, okay, and you go and measure the delta 13C, and we will notice that for certain plants, certain organisms, the delta 13C values are very different, and specifically in Earth's history there is a huge difference when we were having first non-flowering plants, then the entire non-flowering plants got replaced by the flowering plants. So, even though some non-flowering plants exist today, but the flowering plants has totally taken up, and now the dominant they are the dominant plant type in today's world. Okay. So, between the flowering plant and the non-flowering plants, there is a significant difference in the delta 13C values. So, therefore, how the carbon has changed in the past, we can just use the delta 13C value of the soil to understand what kind of productivity it was having at that particular age. So, such studies are very useful. Okay. Such studies are very useful, because to understand changes in aquatic systems are very much dependent on the terrestrial ecosystems. Not only the terrestrial aquatic system like groundwater, lakes, rivers, but also the ocean, because of the supply of terrestrial substances from the continent to the ocean. So, I will stop today in this particular lecture, and we are going to discuss more in the next lecture. Thank you.